lecture about communication protocols. In the previous chapter, we talked about UART and USART and learned how to use that protocol. Did you do the exercises before coming here? If not, you can always go back to maximize the learning outcome of this course. In this chapter, we proceed with another communication protocol called TWI, or also I2C. TWI stands for two-wire interface, while I2C stands for inter-integrated circuit. As the name suggests, this protocol requires two wires. So what are we going to do in this chapter? First, I will show where the I2C interface is located in the ATmega 328P chip. Then we will discuss how the protocol works, how conflicts can occur and how they are resolved, and we conclude the lecture with an example and obviously a practical session. I2C is quite common. The protocol itself is already around for 3 decades, and it supports transfer speeds between 100 kilobit to 5 megabit per second in the latest revision. Examples which use I2C include real-time clocks, sensors and EEPROMs, like the ones shown here. This is a BH1750 sensor mounted on a breakout board for convenience. This sensor measures light intensity. On the right is an EEPROM, an electronically erasable non-volatile memory. At the bottom are 2 real-time clocks or RTCs, which are able to keep track of the time. Often, the RTCs come on breakout boards, which also feature an EEPROM. You can see it here. This is the actual RTC, while this is an EEPROM. Same with this breakout board. While this is the RTC, the EEPROM has been mounted here. I'm going to attach the datasheets for those devices in case you are interested. While the ATmega 328P has also an internal EEPROM, and we will talk how to access that a bit later in the course, it might be insufficient since it is only 1 kilobyte in size. Larger, non-volatile memories might be required while keeping an eye on the power consumption. Imagine a remote battery-powered embedded system that records light intensity. If the battery runs out, it will be okay. However, the already recorded data should not be lost. In this scenario, the measurements could be communicated to another system with a larger memory. However, communications are costly in terms of power consumptions. The other inexpensive alternative are EEPROMs, which come in various sizes of several megabit and are accessible via I2C. Now you can access the EEPROM, the light sensor, and any of the RTCs in this picture using one I2C interface. And that brings us to another difference compared to UART or USART. I2C supports multiple devices through one interface and is therefore also called a bus. So how do you connect the I2C bus? We already handled the RXD, TXD and XCK pins in the previous chapter about UART and USART. So what is left with respect to supported communication protocols are the blue SCK, MISO, etc. and the green SCL and SDA. Well, that sounds about right. Two-wired interface, 2 wires SDA and SCL. That must be it. So pins PC5 and PC4 can be used for I2C communication. We already said that the I2C protocol is a bus system and it supports multiple devices attached to the 2 wires. Here is a schematic representation of the bus. As you can see, we have 5 devices, out of which 2 are masters, which can initiate communication. A master can be the ATmega 328P, and the slaves can be the RTC, the light sensor, and the EEPROM. So how long can be the wires? Can they bridge several kilometers? Unfortunately not. They can have a length of about a meter. However, that depends on several factors, such as the communication speed, wire quality, and if they are shielded. For instance, at 100 kilobaud, 1 meter might work. At 10 kilobaud, maybe 10 meters work. It is about trial and errors. In general, it is said that the capacitance between the 2 wires is to be kept to less than 400 picofarad. The capacitance varies with length, shielding, diameter, proximity to each other, etc. So you have to try. Also, a voltage is to be supplied to both wires. If no device is connected, their potential will be equal to VDD, since the source will charge the wires through those 2 so-called pull-up resistors. So imagine the supply powers the wires through these resistors, hence both of them are idling in a high state. So how will communication work when VDD is connected to the wires like that? Let's have a look into one master and one slave to see what is happening inside. Both are connected to SDA as well as SCL. Imagine that there are little switches whose state, if they are open or not, is somehow controlled. If the bus idles, all switches are open and SDA as well as SCL are in a high state as shown here in this picture. However, in this scenario, the master closed the switch connected to SCL. Now all the potential and charge that is in that wire will be discharged through the switch into the ground. VDD tries to pull up the wire again to the high state. However, the wire is separated from VDD by this resistor. This resistor is, well, it's resisting that pull up. So VDD is not able to pull up the wire to the high state as fast as it is directly pulled down to the ground by the master. If the resistor R2 is omitted, VDD will be directly connected to ground, which represents a short circuit. Hence, always use pull-up resistors. As you can see, the master closed the switch, and since VDD is too slow to pull up the wire to a high idling state, the value on SCL is 0 or low. Since the master has to become active to write a 0 to the wire, this state is also called active low. If this switch is opened again, SCL is kept floating. Since no one discharges the potential of SCL into the ground anymore, VDD is able to charge the wire to its high state as shown in the diagram. So how does the transfer of data between a master and a slave work? Imagine that the control clouds shown in both of them are not only controlling the switches that pull either SDA or SCL down to the ground, but they can also sense if the wires are held in a high or low state. The master has the rights to pull down SDA as well as SCL. The slave, on the other hand, can pull down SDA but can only sense what is on SCL. In this scenario, both wires are held in a high state currently. The master then starts to pull down SCL to the ground. The slave senses that change and knows that the master is going to initiate communication. The master then pulls down SDA as well, which the slave also senses. By repeatedly pulling down SCL and letting it return to its high state, the master is able to generate a clock signal, while the actual data is on the SDA wire. The rule is that the data can only change if SCL is held low. If SCL is released, like in this period, somewhere between this point and this point, the slave will sample the state of SDA, that is, read the value from SDA. The master has to give sufficient time to let the wire recharge to its high potential and to the slave to read the value. So here A0 is written to the SDA line by the master and read by the slave. That means the communication transfers data from the master to the slave currently. To send A1 from the master to the slave, the master has to pull down first SCL to be allowed to change the data on the SDA wire. Then the master can let go of SDA to put it into a high state, that is, writing A1 to SDA. After which, the master has to let go of SCL as well to tell the slave that SDA is ready to be read. Again, somewhere between this point and this point, the data, which is 1 now, is read by the slave. Then, in this example, the master releases SCL to charge the wire, and it also let go of SDA. However, remember, we said that SDA can only change if SCL is low. So this is a violation of the protocol. However, in I2C, this violation is detected by all participants of the bus and indicates a special case, that is, the end of transfer, and tells everyone that the bus is free for the next transfer, which could be from the slave to the master. So how does this direction work if, for instance, a temperature sensor has to tell the master the current value? Let's reset the bus. Both lines idle in a high state. Again, the master pulls down the SCL line, which is recognized by the slave, indicating the start of transfer. However, now the master is not closing the switch for the SDA line, but the slave connects SDA to the ground, since it wants to write a 0 to SDA. If it wanted to write a 1, the slave would not have done anything and let the line remain in a high state. After some time, the master releases SCL, so this wire recharges. Now, no one is allowed to change the state of SDA while the master samples what the slave wanted to communicate, here A0. After the data is sampled by the master pulls down SCL, which is recognized by the slave and allows it to change the SDA line to write a 1, for instance, by opening its switch. As long as the SCL line is high, the slave cannot proceed with the next bit. As you can see, the master determines the clock. So the entire communication procedure looks like this. First, the data is always sampled when SCL is high, like during this period or this period. Second, to start the transfer, a master creates a bus violation. That is, it pulls down SDA while SCA remains high. That is not allowed, since the data is sampled when SCL is high, and therefore SDA must not change. However, this special condition of start of transfer is detected by all participants of the bus, and they get ready to receive the data from the initiating master. Third, once the master completed the transfer, it creates another violation. In this case, it pulls down SCL as well as SDA. And then it lets go of SCL first before releasing SDA. Everybody knows now that the transfer has ended. That means as long as the communicating master does not send the end of transfer condition, the bus is reserved and cannot be used. Even if the master takes a very long time, that is, has a slow clock on SCL, or has a lot of data to be transmitted. Here we zoomed into the start condition. First, SDA changes from high to low before SCL follows, indicating the start condition. And the end of transfer condition, which is the reverse of the start condition. First, SCL toggles from low to high, after which SDA is released. This is also called the stop condition. That is the end of this session, in which we learned how data is exchanged between a master and a slave and vice versa. But we are not done yet. In the beginning we stated that there can be multiple masters and slaves in the bus. So how does a slave know that the data sent by a master is for itself or for another slave? In this session we will learn how the addressing works. Addressing is required since multiple devices could be connected to the bus, and it needs to be established who communicates with whom. Similar, when someone wants to call you on the phone, first a number is dialed to determine the destination of the call. Here we see the entire packet of the I2C protocol. First, it begins with the start condition in pink issued by the master. Following is a 7-bit address of the slave. The addresses of the slaves are usually fixed and can be found in the datasheet of the device. In many cases, it is also possible to choose from, for instance, 3 addresses so that a developer can use 3 EEPROMs on the same bus without address conflicts. Addresses can exist only once in the bus, but do not need to be unique if the devices are on separated buses. Out of 128 possible addresses supported by 7 bits, 16 are reserved and cannot be used. One of the purpose of the reserved address we will see in a minute or two. After the address is a direction bit. That bit indicates if the master wants to write to the addressed slave or if the master wants to read from the slave. The direction bit is followed by an acknowledgement written by the addressed slave. Every 8 bits need to be acknowledged by the slave. To acknowledge that the slave is ready for the next set of data, it pulls down the SDA line. If there is no slave with the address or the slave is not ready yet, the SDA line remains high to inform the master that an error occurred. After the acknowledgement, the data transfer starts. Depending on the direction bit sent earlier, either the master or the slave writes to the SDA line, while the acknowledgement travels in the opposite direction. As long as no stop condition, here in cyan, is sent, multiple bytes, each acknowledged, can be transferred as seen here below. So what about the reserved addresses? Some of them are used to expand the address space. There are slaves which have a 10-bit address instead of a 7-bit address to increase the number of supported devices per bus. However, both kind of slaves can be mixed and be attached to the same bus. Therefore, the I2C protocol has to make sure that no 7-bit slave reacts to the first 7 bits of a 10-bit address. Therefore, no 7-bit slave has the address starting with 4 ones followed by 1 0 and any other 2 bits. For instance, the addresses 11110000 and 11111010 are reserved. These initial 5 bits do not count for the 10-bit address. 10-bit address slaves are aware of that and expect the address to follow those initial 5 bits, occupying 2 bytes in total, as shown in the figure below. If the master wants to transfer data to the slave and the direction bit is 0 as shown here, the remaining transfer remains the same. However, the transfer method becomes more complex if the master wants to read from the slave. First, the master has to send the start condition as usual, followed by the bit sequence 11110 to indicate the 10-bit address. After the 2 most significant bits of the 10-bit address, the direction bit follows. Since the master is not yet done transferring the complete address, it wants to write the second byte of the address to the slaves. So, a 0 is in the direction bit. After the acknowledgement, the master writes the second byte, or in other words, the remaining 8 bits of the 10-bit address, which is again acknowledged by the addressed slave. However, the slave is in a I have to receive data from the master mode by now. To change the mode without letting go of the bus, which then could be reserved by another master, the very same master sends again a start condition without terminating the transfer. That second start condition is called a repeated start. This start is followed by the bit sequence 11110 plus the first 2 bits of the 10-bit address to make sure that no 7-bit slaves interfere. The next is the direction bit, which is set to 1 by now, since the master wants to read from the slave. That is acknowledged by the very same slave that has been addressed in the first part of the transfer, namely this one. Finally, the communication pairs have been established and the slave is able to transfer its data. Let us finish this session with a few key observations. First, 2 wires are required for I2C, transferring data serially similar to UART. It uses the same line for reading and writing operations, so it is always half duplex and not universal. However, compared to UART, which always comes in a transmitter and receiver pair and is therefore considered to be a point-to-point connection, I2C is a bus system and multiple devices on the bus are supported. And I2C has an acknowledgement mechanism that is not available in UART. Imagine a simplex system in I2C and UART, despite the fact that there is always a transmitter or master in I2C and always a receiver or slave in I2C. The slave is able to tell the master if the data transfer was successful. That is not possible in UART, as the receiver has no method to tell the transmitter that the data has been received successfully, or if, for instance, bit flips occurred. On the other hand, I2C does not support parity, which then needs to be implemented in software if required. That's all regarding the addressing. In the next session, we are going to show what happens if two masters want to communicate at the same time and how this conflict is resolved, like in this scenario shown here. How is this conflict detected and who will proceed? Let's have a look at the values of the wires. Imagine both masters send the start signal, so both close the SDA switch first, followed by connecting SCL to the ground. The values on SDA and SCL will be the same, no matter how many times they are connected to the ground, through 1 or 2 or a million masters. Therefore, so far, no conflict is detected. Let's say the slave address both masters would like to communicate to starts with the most significant bit set. So both masters are going to put a 1 on SDA and release the SCL line so that the slaves can read the first bit. The next address bit of the slave is set to 0 for both masters. Again, the value on the bus is as expected, that is 0, and no conflict occurs. However, the next address bit differs. Master 0 wants to communicate to a slave whose address starts with 100, while the destination of master 1 begins with 101. Therefore, master 0 closes the switch for SDA to write a 0, while master 1 leaves it open. Since SDA is connected through master 0 to the ground, the value of SDA becomes 0. Both masters sense the SDA line for instance, the acknowledgements and data coming from the slave. However, if a master writes to a line, the same mechanism is also used to listen if the written value matches the read value. While this is certainly the case for master 0, which writes a 0 and senses a 0, it is quite different for master 1. It writes a 1 to SDA but reads a 0. Therefore, master 1 recognizes that there is something else holding onto the bus and a conflict is detected. Therefore, master 1 drops out of the communication and waits for the stop condition for a retry. Okay, that's all about conflict resolution, which is done quite elegantly and automatically. In the next session, I will show how to configure I2C to use in an ATmega 328P. If the MCU is a master of the I2C bus, it needs to generate a clock signal for the SCL wire. Like the transfer rate configuration in UART, the frequency of the I2C bus needs to be configured as well. The frequency is computed by this formula. It depends on the system clock of 16 MHz in case of Arduino, the desired frequency of the bus, and a prescaler P. Again, the result needs to be an integer that fits into the 8-bit of the TWBR. The prescaler can be either 1, 4, 16 or 64. While the TWBR takes care of the SCL line, we have to know what data is to be transmitted. That data is in the TWDR. That is either the data byte or the slave address with the direction bit summing up to 8-bit as well. Please note that this register can only be written if TWINT, which I'm going to talk about in a minute, is set. Please check TWINT before writing to TWDR. If the MCU reads from the SDA wire, the data is shifted in, and hence TWDR contains the last data received. The next register is the TWI status register. Unfortunately, I2C is not as comfortable to use compared to UART, and we will see in a minute the reason why. The status register is divided into two parts. On the left are the status bits, and on the right, separated by a reserved bit, the prescaler. Let's start with the latter one. We have 4 options for the prescaler to be configured with the 2 bits. There is no option to turn off the prescaler, and either of those values shown here must be chosen for the desired SCL frequency. Please have a look at the quiz to know how to choose an appropriate one. The left side of the status register informs us about the status of the I2C hardware unit. First of all, there are 4 modes available for the ATmega 328P. First is the master mode, in which the MCU is the master of the I2C bus, able to initiate a data transfer. Then that master has 2 submodes. It can either read from or write to the slave. Another 2 modes are available if the MCU is a slave, and if that slave submits or read data to or from a master. Hence 4 modes, and based on the chosen mode, the status bits can have different values. Let's start with the MCU being a master and it wants to write to a slave. One note: if the TWSR is red, please mask out the prescaler bits, as they are not required to know the state. Okay, if the start condition has been transmitted successfully, the status bits will carry the value 8 in hexadecimal format. As a software developer, you have to wait for the status to be 8 before continuing with the slave address and the direction bit. If the address has been transmitted together with the direction bit, here a W, as we want to write to the slave, the value is based on if the master received an acknowledgement or a non-acknowledgement, and it is up to the software to react to it. If the master received an acknowledgement, then the master has a few options: transmit the data bit, send a stop condition and therefore release the bus, send a repeated start condition, or just wait and do not do anything, reserving the bus. What is done is totally up to you. If the address and the direction bit is replied to with a NAC, then maybe the slave was busy, offline, or just not ready to talk to the master. Again, what the master does with that information is totally up to the software developer. The same is true for the data bits to be transmitted. If the master loses the bus because 2 masters send at the same time, the status bits will be 38 in hexadecimal format. If the master reads from a slave, the status bits are different. While the first three are the same, we have new ones, depending if the address bit and now the direction bit carrying a read request is acknowledged or not. For the data bits, the master transfers the acknowledgement and informs the software side if it was successful in doing so. For the slave mode, there are again different status bits. If your MCU is running in the slave mode on the I2C bus, I would like to refer you to the attached datasheet, which contains tables with the status codes for the remaining two modes. The principles will be similar, hence we omit the slave mode in this chapter. Okay, here we have the control register, which determines what is being sent out to what the status register reacts to. The first two bits are the TWINT and TWIE bit. TWINT is the interrupt flag, and it is set if the I2C hardware is ready to process the next byte. That can be after, for instance, the start condition has been sent successfully or a data byte is transferred. If global interrupts and the TWIE are set, an interrupt request is issued. However, please keep in mind that the interrupt request is not cleared by serving the ISR as we have seen earlier, in which, for instance, the compare match of the timer interrupt was automatically cleared once the ISR has been completed. The clearing of the TWINT needs to be done manually, and here is another curiosity. It is cleared by writing a 1 to it and not a 0. As soon as it is cleared, the data from the TWI data register is read. So before clearing TWINT, make sure that the data register is loaded with the next byte and the status has been checked. While you get ready for the next data to be transmitted, the I2C hardware unit automatically stretches the SCL low signal on the bus. The TWEA bit configures if an acknowledgement is returned or not. If it is set, the master will automatically acknowledge each read data byte from the slave. In slave mode, the acknowledgement is sent if the address has been detected and a master wants to talk to this MCU. If TWEA is cleared, an acknowledgement is never sent. Hence, the device becomes unavailable temporarily as it never acknowledges the received data. If TWSTA is set, the I2C unit checks if the bus is free, and if so, sends the start condition to claim the bus. If the bus is not free, it waits till it recognizes the stop condition. Once the status register informs that the start condition has been transmitted, the TWSTA bit needs to be cleared. The TWSTO bit is the stop condition. Once all data has been written to the slave, the master has to send the stop condition to release the bus. This bit is cleared automatically once the stop condition is out. In slave mode, if something goes wrong with the I2C hardware unit and you would like to reset it, you can write this bit to bring back the I2C unit to a known state. Ideally, the TWWC bit is never set. It describes an error condition in which the software already accessed the TWI data register while the I2C hardware unit was still busy transmitting something such as the slave address. Before modifying anything, please make sure that TWINT is set. Nothing is going to work if TWEN is not set, as this bit activates the I2C hardware and connects the two pins PC5 and PC4 to it. In case the MCU is a slave or a master and slave combination, you will need to set the slave address in TWAR. If you would like to use 10-bit addresses, it needs to be implemented entirely in software. It is probably a good exercise. The slave address is left adjusted, leaving the 0th bit available. This bit is set if a general call is to be supported by the slave. If a master transmits to the slave address 0, a broadcast is issued on the bus. That means that the master communicates to all slaves which support general call, while the master has no idea to know how many slaves receive the broadcast. Another register is the address mask register. Usually, a slave has only one address. However, many times a slave can have multiple functionalities. For instance, your ATmega can be connected to a light and a temperature sensor. While both data can be sent back to the master and let the master decide which it needs, the MCU can have 3 different slave addresses. The first slave address reports only the temperature, the second the light intensity, while the third address reports both. The bits in the mask register state which bits in the TWAR are to be ignored during the address matching. That was quite a bit. As you can see, a lot more needs to be checked and manually configured to access the I2C bus compared to UART. Let's have a look at it, how to implement a master in the next session. In this session, we will go through the programming of an I2C master step by step. This master should be able to access a slave on the bus and read out the data. But before we start, we have to build our bus. That brings us to the question what the sizes of those 2 pull-up resistors are supposed to be. How do we select them? These resistors can be in a range. First, let's compute the lowest possible value. It is determined by the bus voltage, the voltage which is still recognized as a logical 0, and the current that the pins can sink. Despite the fact that we work in a discrete and digital space, the physical world does not recognize only black and white, but an infinite amount of gray shades in between. Same with the voltage on the bus. Usually we say, if the voltage is 0 volt, it is a logic 0. If it is 5 volt, it is logic 1. But where does this transition happen? What about 0.1 volt or 0.67 volt? VOL describes the maximum voltage that the ATmega 328P still interprets as a logic 0. If the bus is connected to the ground, a current flows from the source through the pull-up resistor, through the bus wires and the device into the ground. There is a limit on the current that can be handled by the pin. IOL describes the maximum current that can go through that pin to pull the bus wire down to 0 and hold it there. The values for those variables can be extracted from the datasheet. Here we see VOL stating that anything between 0 and 0.4 volt is interpreted as a logic 0. And it even says IOH, which is 3 milliamps here. Since the bus runs at the standard Arduino voltage of 5 volt, plugging in these values gives us the lower threshold of the resistor at around 1.5 kilo ohm. Do note that this is a physical limit of the pin and it is independent of the bus characteristics. The only value to adapt the 1.5 kilo ohms that can change is V-bus. Alright, what about the upper limit? It is a bit different. The resistance is determined by the rising time of the signal divided by the bus capacitance. How to get those values? Fortunately, those values are mentioned in the I2C specifications, which are also attached to this session. As you can see here, the rising time for a bus running at the maximum frequency of 100 kHz is 1000 nanoseconds. For the faster bus at 400 kHz, the rising time reduces to 300 at maximum. And here is also the bus capacitance of 400 picofarad. Alright, let's plug those values into our formula. If the bus runs at 100 kHz, the maximum resistance that is officially supported is 2.5 kilo ohm. That means for such a bus, you can choose a resistor between 1.5 kilo ohm and 2.5 kilo ohm. However, if you want to run the bus at 400 kHz, the maximum resistance is only 750 ohm. That is below the minimum resistance of 1.5 kilo ohm that we computed earlier. Also, having a look at the current of a 750 ohm resistor connected to a 5 volt source, you see that 7 milliamps will go through it. However, the pin can sink only 3 milliamps without damaging itself. So the physical constraints are violated. So what to do? Well, we can lower the clock of SCL or the bus supply voltage V-bus. There is another way though. The bus capacitance of 400 picofarad represents the worst possible case in the I2C specifications. So how much capacitance does the bus usually have? Let's say you would like to connect two ATmega 328P through an I2C bus. The datasheet says that the pin capacitance is somewhere between an unknown value and 10 picofarad. That means if I have two Arduinos, the capacitance is around 20 picofarad, ignoring the wire capacitance of the bus. Usually the capacitance of a pin is around 7 picofarad, so 10 picofarad is again the worst case. What happens if I use 20 picofarad instead of 400 picofarad? The resistor value increases tremendously to 50 and 15 kilo ohm for the 100 and 400 kilohertz bus frequency respectively. The current reduces to 100 or 333 microampere, a much healthier value for the pin to sink. So now a developer can choose between 1.5 kilo ohm and 50 kilo ohm for the 100 kilohertz bus. But which one? A lower resistor value closest to the 1.5 kilo ohm ensures that the bus is charged a lot faster, and hence it supports a faster clock as seen in the upper waveform. External noise does not affect the bus much, since any loss in charge is replenished almost immediately. However, as we saw, it also results in a higher current, meaning if the system runs off a battery, it is drained faster. If the developer decides to save battery power and chooses a higher resistance, the bus does not support fast clocks any longer, because the recharging of the bus takes longer as shown in the lower waveform. In addition, the bus might be more susceptible to noise. So the developer has to compromise and find out the right values by trial and error or by using an oscilloscope to check the waveforms. Those waveforms should be nice and squared. The lower the resistor values, the more rectangular are the waveforms, but at the cost of an increase in current. Another parameter included in the trial and error is the clock generated by the master. For instance, if the datasheet of a device states that it supports 100 kHz, it does not mean that it has to run at 100 kHz. That is in contrast to UART that we had in the previous chapter. Since the master generates the clock, the slaves dance to that rhythm. If it is slower, the data transfer rate reduces, but it gives also more time to recharge the SDA line from logic 0 to logic 1. Once enough time has passed, the master can then release SCL to recharge it as well. Once the voltage of SCL crosses the threshold, the slave will sample the SDA line, which has been fully recharged by now. One obvious source of error are loose or weak connections, so check those as well if the bus does not work. One thing that I'm reading in the internet often is the usage of the internal pull-ups. Remember from chapter 4? I showed this diagram briefly mentioning PUD. If PUD and the DDR are set to 0 while a 1 is written to the pin, this transistor connects VCC through this resistor to the pin. This resistor is usually in the range of 30 to 50 kilo ohm. So it might be a bit too high to work, but nevertheless you can try. If it does not work, however, connect external resistors to the bus lines to remove one possible source of failure. Let's start with the implementation. If you do not have an I2C device, you can use the attached binary. It is a program that makes an Arduino an I2C slave. So instead of an I2C sensor, you require two Arduinos, one that we program as master and the other one executing this slave program. The address of the slave Arduino is 12 in hexadecimal format. If you write a 1 to the slave, it will turn on the onboard LED. A 0 turns it off again. Okay, with all that theory about building an I2C bus, let's dive into the programming part. Okay, let me show what we have here. This is an Arduino, this is my master, and this is a FreeDuino, which is basically compatible with the Arduino, and this is supposed to be my slave. As you can see, the FreeDuino is not connected to any USB power supply. The power in this case comes from the Arduino, from the master, so these two wires, so they are connected to 5 volt and ground. This is the 5 volt wire, the red one, and this is the ground. Then I connected PC4 and PC5 to PC4 and PC5 of the slave Arduino, without any pull-up resistors, because I want to use the internal pull-up resistors of the master. For the practical session, we can go to course, I2C and Blink. There are two directories, one for the master, one for the slave. Let's have a look at the slave first. It does not contain much. Let's have a look at the C file. I'm using a library in this case, and I have I2C received for a received character, and I can even request data. However, in this case, if I receive a 1, I want to turn on the LED, the onboard LED. If I receive a 0, then I turn off the onboard LED. Here we use the internal pull-ups. If use int pull-ups is defined, and currently it's not, it has been commented out. In case it is defined, the pull-up disabled signal is reset. That means it is enabling the pull-up. Then I have to put a 0 in DDC4 and DDC5. These are the PC4 and PC5 pins. And I have to write a 1 to the ports to activate the pull-ups. I'm calling a library function called I2C set callbacks. These two functions are then called in case a character has been received or requested, and this is a pointer to these two functions here. Then I initiate the I2C slave with I2C address, which is 12. And in the main loop, I don't do anything. Important to note is the I2C init automatically shifts the address by 1 to the left. Let's have a look into this. I2C init, here is the address in TWAR. The address is sent and it's shifted by 1. As you can see, it uses interrupts to react to different states after, for instance, receiving the start condition or the address. The link to this library I'm going to add to the resources folder on your right. So if you don't have a I2C sensor or device, slave device, you can use this, the blinking I2 slave.elf, and upload it onto a second Arduino, turning it into an I2C slave device, reacting to address 12 in hexadecimal format, and it accepts 2 characters. That is basically the 0 to turn off the onboard LED and the 1 to turn it on. Any other character will be ignored. On the other hand, we need also a master, so I'm changing the directories to master. There are a few more directories available. Blinking I2C master is the directory we are going to work on in a little bit. Then here is an Arduino implementation using the Arduino library, and here is an I2C master library that I downloaded from the internet. I'm going to add the link again into the resources folder. Let's have a look at the blinking Arduino, how they implement this. In the setup function, I have a wire.begin, which essentially activates the I2C bus, and then I have a begin transmission with a slave address that I want to communicate to. I write a 1 to it, and then I have the end transmission, which essentially creates a stop condition. So this program you can copy into the Arduino IDE, upload it on another Arduino to make it a master, and try it out. If you connect it to the slave Arduino, it should make the LED blink. Please note that wire.begin uses the internal pull-up resistors as shown here. Let's have a look how it looks like. Let's see where this C file is located. And we have here a library. In the libraries, so there should be somewhere a init. Search for it. It starts with the wire.begin. There's then this function call, and there is nothing much, but there is a TWI init. Let's see what that is. At the same time, we see here that TWI.h is included, so I expect that TWI init is somewhere in this file. Let's search for it. And we have a TWI.C. And there should be a init. I think it's the first one. TWI init. And here you see that the internal pull-ups are activated. If you use the wire library, you have to adapt the external resistors or even remove them. Okay, let's start writing our program. Currently there's not much in this directory. There's a makefile that I already added and a blinking LED master, which is currently of 0 size, so nothing is inside. Before we start programming, let's have a look at the AVR library. And I already bookmarked a link here. There is a util twi.h. I'm going to add this bookmark also into the resources folder. So here we have some help. We see some defines like TW start and so on. These numbers match the status numbers that we had to check out if, for instance, the start condition has been sent successfully. TW, which stands for 2-wire, and MT, that is one mode, so the master transmitter, and we have a master receiver, and we also have a slave transmitter and a slave receiver. So these are all the states. Let's have a look at the lecture slides in which we discussed them. So we have here the status bits TWS7 to TWS3 from the status register, and you see that these numbers match exactly the numbers given here. So this is start transmitted and it's TW start. Or here arbitration lost. The bus is 38 in hexadecimal, and we have the same number here for master transmitter and master receiver. And we have a little bit more help. Scrolling down a bit, we have here the TW status, which is essentially the TWSR register. That is the status register for the 2-wire interface, and it's logically ANDed with the TW status mask, which is just below that. It's basically the TWS7 till the TWS3, and it's ANDed with that, so I get only these bits here. Further, I would like to point out the reference manual for the ATmega 328P. There is a chapter about the 2-wire serial interface, and it contains everything that we had in the chapter so far, but it also contains an interesting figure, namely this one. So it says here that the application writes to TWCR, that is the control register, to initiate the transmission of start, and then it says, okay, the start, it has been sent, and TWINT is set once the start is over. The status code indicates that the start condition has been sent, and then it says here what I need to do. So TWSR, I need to check if start has been sent, and then I load the slave edges in, for instance, the right direction bit to TWDR, and then I continue with loading the appropriate control signals to TWCR. At the same time, I have to make sure that TWINT is written to 1 to clear it and to initiate the next transmission of SLA plus W. So while we write our master program, we keep referring to this figure here. Alright, let's dig in with our blinking I2C master. As a first step, I want to include the helper utilities, that is TWI.h if I'm not mistaken. Can the check it once, is util TWI.h, which makes all these numbers available for me. Then what I also define is the slave address, which is 12. However, the 12 needs to be shifted by 1 to the left, because the least significant bit of this entire byte, so we have 7-bit slave addresses, and the least significant bit of the entire byte is reserved for the direction bit. Let me define this direction bit immediately. I2C write, which is 0, and we define I2C read, which is 1. So if I want to write to slaves, I use I2C write, and if I want to read from slaves, I use I2C read. Then, in case I want to use the internal pull-ups, just put everything into a hash if-def, so that I can easily turn it on and off depending on the needs. And this is my header. Now we need the main function. What I want is the master to make its onboard LED blink as well, so that I see that something has been transmitted. That means, as we had it before, I configure this to be output pin, and if I want to use the internal pull-ups, I make them in if-def and then use in the pull-ups. So in case this is defined, this code is added. For the internal pull-ups, let's consult the manual once more. POD, let's search for POD and where it is located. Yeah, so POD is in the MCU-CR, this is the MCU control register. Somewhere should be mentioned what it means. Oh, I think here it is mentioned already. The POD bit in MCU-CR disables the pull-up function for all the pins in all ports when set. That means I have to make sure that POD, the POD bit in MCU-CR, is set to 0. So let's do that. MCU-CR. POD. So I ended with not POD bit to make sure that everything stays the same except the POD bit. Then the direction register for C. Remember that the I2C interface is connected to PC4 and PC5, and the direction bits need to be set to 0 as well. Let's see. There's a fourth one, and let's see, 5. So that leaves everything intact except PC4 and PC5, which are then set to 0. And I have to write a 1 to both of the pins. C5. And that's it. As a first step, let's initialize the I2C bus. Initialization includes setting, for instance, the SCL speed. So let's hide everything in a function to keep it neat and clean. To set the speed, let's have a look how to do that, and for that I refer to the lecture slides. So we have the formula here over here with the prescaler 1, 4, 6 and 64, and TWBR must be an integer. So let's assume the prescaler is 1, so I make this formula very simple. Let's see how I set it to 1. That means TWPS1 and TWPS0 must be both 0 to have a prescaler of 1. For that I have to write it to TWSR. I don't have to care about these bits at all. TWSR equal to 0. That makes sure that the prescaler bits are definitely set to 0. And then PWBR, that is equal to so we have the frequency, which is in F CPU, divided by 2 times the frequency of SCL, SCL into 2, and then minus 8. To make it more readable, I define it like this, and that sets TWBR. So this hasn't been defined yet, so let me define this. Define FSCL, and I'm using 100 kilohertz. Done. If this is computed, so this is 16 megahertz divided by 100 kilohertz into 2 minus 8 should be equal to 72. Alright, now I would like to communicate to the slave. That means I want to send a start condition. For the start condition I have to write to the control register, but the question is, what do I have to write? Let's go back to the lecture slides. TWCR. I definitely have to set TWEN to 1, which activates the I2C functionality. I have to set TWSTA, which sends the start condition, and I have to tell the I2C hardware unit that everything has been set and everything is ready. That means I have to clear TWINT. That is called the TWI interrupt flag. And A1 is clearing it. In this master I'm not using interrupts. This can be a good exercise to convert everything using interrupts. So let's write it. So I have to activate it. I have to set the start condition bit, this TWSTA, as far as I remember, and at the same time I can commit the changes, this is TWINT. And that sends the start condition. Now before sending the slave ages and the direction bit, I have to make sure that the start condition has been sent successfully. And once it has been sent, this TWINT bit will again be equal to 1. So I just have to wait till this bit is set again. So I have a while. TWCR and 1 or BV TWINT and the entire expression as not. So let me comment this. Read and this is sending start condition. So as long as this bit is not set, the start condition has not been sent out yet. If it is set, then I can proceed with the slave address. However, first I have to check the status register if the start condition has been sent successfully. Sent successfully. And I do that by checking if the status register is either on TW start or TW rep start. In this case, I don't care if it's start or repeated start. So I check for both of them. So let me save this in a variable. Remember, this is the TWSR register with the prescaler bits masked, so they are not checked. And if this status register is not equal to TW start, or TW rep start, then something was wrong. Put the brackets properly and let me return an error. Return 1. So I have to change the return value. If it was successful, then the status register is either TW start or TW rep start, and I can continue with the slave address. So in the documentation, we are right here now. Let me go back to that figure. Here. So we set the start condition, and this TWINT is set. When I come to this line, because I'm checking here and I'm waiting till TWINT is set. If it is set, I check if the status register is equal to TW start or TW rep start, which is set here. Check if TWSR is set to start, if a start has been sent. And then the application, that is the program, loads the slave address and the direction bit, that is the write, into TWDR. Okay, let's do that. TWDR is equal to the address. So let's make it more universal, because I might communicate to other slaves as well. And I expect a parameter. This is the address. It means I have to add the slave address here, and that is my address, which has been already shifted by 1. TWDR also contains the direction bit, which is a 0 in this case, because I want to send either the 0 or the 1 to the I2C slave. But out of completeness, what I can do is write. So now this address, which has been shifted by 1 to the left, so the least significant bit is available, and I add 0 to it, that means I don't change anything. Or if I want to read from the slave, I write this. That means I have the address plus 1. That means the least significant bit is set to 1. Okay, so TWDR is loaded with the address plus the direction bit. What else do I have to do? Then I have to load the appropriate control signals to TWCR. And I have to make sure that TWINT is again set to 1, because we are ready to transmit the address plus the direction bit, and TWSTA which is not reset after the start condition has been sent, is written to 0. So then we are right here in our protocol. So let's do that. TWCR is equal to, so commit the address and keep it active. Because I'm setting the equal sign here, automatically this TWSTA will be set to 0. Again, I have to wait till the address has been submitted. Oh, there's a little misspelling. Let me comment this. Including direction bit. Let me correct the spelling here. It looks nicer. I can wait till this has been sent, and then I check if the address has been sent. So again, check if address has been sent successfully. TWSR, TW status, now I'm expecting the status register. Oh, T, sorry, it's T. Let me check. That is either the master transmitter, SLA acknowledged, or in case I wanted to read from the slave, then the master becomes a receiver and I have to check for this value. So I'm expecting either 18 or 40 in the status register, and if this is not the case, then some error occurred. TW and T slave acknowledgement. Either this one. TW master receiver slave should also be acknowledged. If this didn't happen, I have an error and a return 2. Otherwise, no error occurred and I can return a 0. So right now I'm here checking for this acknowledgement, and then I'm right here. So TW in INT has been set, and the status code indicates that SLA plus the W has been sent and the acknowledgement received. So I'm checking if this was the case. Now what happens next? The application loads data into TWDR and loads appropriate control signals into TWCR, making sure that TWINT is written to 1. So now I'm start to send the data. So let me put this again into a function. As let's see, write. And what do I want to write? Some byte. Okay, it said in the documentation that I have to put the data into the TWDR. Copy data into the data register TWDR. TWDR is equal to data. Simple as that. To send the data, I have to set the signals accordingly. So TWCR equal to, so commit the changes, start transmitting, and stay active. If I don't write this, then the I2C interface will be deactivated because TWEN will be set to 0. TWEN. Again, I have to wait. This transmitter. And we had this earlier already here. And once it is transmitted, I have to check the status register again. And in this case, let's check the AVR library documentation. That means I'm now at the transmitter and I expect a data acknowledgement coming back. That is 28. So the status should have the 28. TB status. If that is not the case, then an error occurred and I return 1. Otherwise no error occurred and I can return a 0. So now I can send a 1 and a 0. I2C write a 0 to turn off the onboard LED, and I want to send a 1 as well. And in between I wait for, let's say, half a second. However, I also have to send a stop condition. This will be a repeated start condition, but I have to release the bus. So I have an I2C stop. Same here. Although currently there's only one master and one slave, therefore I can also write it like this without releasing the bus at all. Because I have a point-to-point connection and nobody else can reserve the bus. So this will be the same in this scenario. However, if you have multiple devices, you should release the bus. Okay, so let's implement I2C stop. No parameter so far. Alright, let's check the documentation. So we sent the data, we have the acknowledgement. This TWINT was set because I just waited for it here. So definitely TWINT is set and the I2C hardware unit is ready to receive the next instruction. We also checked the status register and see if the data has been sent and the ACK, the acknowledgement received. Right, so I'm going to do this right here. That means I'm right here. So the application loads appropriate control signals to send stop into TWCR and make sure that TWINT is written to 1. As an alternative, what you can also do, check out the next data. So put the next byte into TWDR and load the appropriate control signals. But now we want to send a stop, and how to do that. Let's check out the documentation again from the lecture. So I have here this TWSTO, which is the stop condition bit, and it is cleared automatically. Yeah, and that's what we need. So it's TWCR is equal to TWINT, telling the hardware unit please transmit, please stay enabled, and please send the stop. stop condition. Then we wait for it. Wait till is transmitted, and then that's it basically. Now the bus has been released. To make all these names available with the registers, I have to include some more files. As usual, include avr-io.h and include util delay, because I'm using the delay function. And that's it. Let's compile and try it out. Oh, I have to finish this one. So. Since I'm using internal pull-ups, what I'm trying with the bus is connecting PC4 to PC4 of the slave and PC5 of the master Arduino to PC5 in the slave, directly without external pull-up registers. And let's compile it and try it out. I made a mistake here. I forgot the number. Okay, let's see if it works now. Let's see what kind of interface it is using. ACM2. Okay, let me adapt the makefile. Okay. And does it work? Not at all. Okay, so let's have a look what went wrong. So first of all, I want to make the LED blink. I forgot this, so let me add it. Turn off in this case. B5. And turn it on. So let's have a look. Is the address correct? That is 12. Okay, this is the write, that's the read, that's also correct. Is the speed correct? That looks like 100,000. Okay, I'm sending the start condition by setting TWSDA, and I wait till the transmission is completed. Then I check if it was a start condition or a repeated start condition, if that was successful. After which I load the address with the direction bit. I again commit the changes, I wait till it has been transmitted, and I again check the status if I receive the acknowledgement. That looks very much exactly the list that I want to do. If I want to write something, I simply send it to dr, commit the changes, wait till it has been submitted, and wait till I get the acknowledgement. Okay, that also looks good. What if I never release the bus? So I set the stop condition, and then I wait till the stop condition is transmitted. Hang on a second. Unfortunately, there is no additional information here. Let's see. Oh, okay. So a little sentence here. Immediately after the application has cleared TWINT, that means I wrote a 1 to it, the TWI will initiate transmission of the stop condition. Note that TWINT is not set after a stop condition has been sent. That means I cannot check TWInt if the stop condition was successful. Instead, what I can do, it is written here that it is cleared automatically. That means I just wait till this has been cleared. Alright, a little mistake. TWSTO, and it has been cleared. That means this entire condition becomes 0. Okay, let's try it out once more. Let's see if it works now. So now the onboard LED of the master is blinking as well as the slave. So I would say that was a success. That concludes the session of the blinking LED master. I'm suggesting to copy these I2C functions into a separated file so it can be included into other files easily. What I also want to point out is the blinking I2C master library, in which there is a TWI master.c which already implemented the I2C start wait, that is a start condition, and then it waits if the bus is busy or the device is busy and retries. And we have also here repeated start, and apart from the I2C write, the I2C read acknowledgement to request more data from the device, or the read not acknowledgement, which read 1 byte from the I2C device, and the read is followed by the stop condition. That means no more data is requested. So this library is available in the internet. I'm putting the link into the description or into the resources folder. This concludes the session with the practical blinking I2C master. So what did we do in this I2C chapter? We talked about the protocol and figured out that I2C is a bus system that supports multiple masters and slaves. Since so many devices can participate in the communication, a conflict resolution is required. In I2C, this has been solved quite elegantly by allowing the master to reread the data and compare it with the written data. If there is a mismatch, another master uses the bus at the same time. We talked about how the bus is reserved using the start condition, how it is released by sending the stop condition, and how the addressing works. Extensively, we talked about the resistors, since the control of the bus system is mainly accomplished in software, and in the end, we wrote a program implementing an I2C master and converted it to a library so that we can use it in other programs easily. So what is next? So far, we introduced the UART and the I2C protocol. The next protocol in the list is the SPI protocol, which also has a hardware unit integrated into the ATmega 328P. Although SPI is not that often used compared to I2C, it is required especially if SD cards are to be accessed, as their protocol is SPI. That's all for now. Please have a look at the exercises at the end of this chapter. It is quite interesting. The Arduino slave program reacts to another slave address apart from the given one at 12 in hexadecimal format. It is your task to implement an I2C scanner to figure out which address that is. Have fun and enjoy. Thanks for watching, and I'll see you in a bit.